to all. This is Vaishnavi, Assistant Professor, IT Department from SNS College of Engineering. Now we are going to see about the virtual memory in operating system. Virtual memory. It is a technique that allows the execution of processes that may not be completely in a main memory. Advantages. It allows the program that can be larger than the physical memory. Second one, separation of user logical memory from physical memory. Third one, allows the processes to easily share the files and the address space. Fourth one, allows for more efficient process creations. Next one, virtual memory can be implemented using the demand paging and the demand segmentations. Demand paging. It is similar to a paging system with swapping. Demand paging. It brings the page into the memory only when it is needed. To execute a process, swap that entire process into the memory rather than swapping the entire process into the memory. However, we use the lazy swapper. Lazy swapper, that is, never swaps the page into the memory unless that the page will be the needed. Advantages: less input output needed, less memory needed, faster responses and the more users. Next one, basic concept. Instead of swapping in the whole processes, the pager brings only those necessary pages into the memory. Thus, it avoids the reading into the memory pages that will not be used anyway. Next point, reduce the swap time. Third one, reduce the amount of physical memory needed. Next point, to differentiate between those pages that are in the memory and those that are on the disk, we use the valid invalid bit. Next one, valid to invalid bit. The valid to invalid bit is associated with each page table entry. Valid associated page is in memory. Invalid, that is invalid page, valid page, but it is currently on the disk. Next one is page fault. Access to the page marked invalid causes the page fault trap. That is, determine whether the reference is a valid or invalid memory access. Second point, if the reference is invalid, then terminate the process. Third one, if the reference is valid, then the page has not been yet brought into the main memory. Fourth one, find a free frame. Fifth one, read the desired page into the newly allocated frame. Sixth one, reset the page table to indicate that the page is now in memory. Seventh one, restart the instructions that was interrupted. Next one, pure demand paging. Never bring the page into the memory until it is required. We could start the process with no pages in memory. Next one, when the OS sets to the instruction pointer to the first instruction of the processes, which is on the non-memory resident page, then the process immediately falls for the page. After this page is brought into the memory, the process continue to execute, faulting as necessary until every page that it is needs is in the memory. Next one, performance of the demand paging. Let P be the probability of the page fault 0. P1, effective access time, that is EAT is equal to 1 minus P into MA plus P into page fault time, where MA is the memory access, P is the probability of page fault. The memory access time denoted MA is in the range of 10 to 200 ns. Next one, a page fault caused the following sequence to occur. First one, trap to the OS. Second one, save the user registers and the process state. Third one, determine that the interrupt was the page fault. Fourth one, check whether the reference was legal and find the location of the page on the disk. Fifth one, read the page from the disk to free frame, that is, wait in a queue until read request is serviced. Wait for the seek time and the latency time. Next, transfer the page from disk to the free frame. Sixth one, while waiting, allocate the CPU to some other user. Seventh one, interrupt from disk. Next one, save the registers and the process state for the other user. Next one, determine that the interrupt was from the disk. Next one, reset the page table to indicate that the page is now in the memory, and then last one is wait for the CPU to be allocated to this process again. Thank you.